Anyone haven't signed their name yet?
Yes. I mean, it's just 11.
Yeah, 11:05 is late. If you late more than 6 times, you're not allowed to get A. But even though you didn't late for 6 times, you are allowed to get A. You need to get the score to get A too. Okay, call them. Jia Cheng, Sweta, Yahweh Cheng. Who else? Tolani. Can you call Tolani? Who else is missing? Okay. About homework, right? Homework is exactly the same as in the lecture. Une, did you do homework? You start? What is your progress? Can you share with us? Vega, what is your progress on homework?
I've done the derivation of the first one.
You finished the first question.
No, I haven't taught it yet. But finish like that.
Did you plot the velocity profile?
No, I haven't done it yet.
Do you know how to plot the velocity profile?
I'm not exactly sure like which parameter to vary about it. But
Okay.
because like when you plot against the real number, do you vary the speed?
Velocity profile means velocity versus radius.
Radius?
Yes, that's velocity profile.
Okay.
The equation that I gave it to you is velocity versus radius. You remember v plus equal to y plus for v plus less than 5? You remember that?
Yeah.
First, you will have to come up with your average velocity. Whatever you select, you may say 2 meters per second. Okay, that's your average velocity. You can use 2.5, you can use 3, you can use.
You can select also.
But you need to select yourself. Okay, it is not given. And you need to come up with your viscosity, your own viscosity, your own density. Okay, viscosity, density, and pipe radius, yes. So when you get all that, can you calculate Reynolds number, rho VD over mu? Yes, you can, right? And you need to make sure that that Reynolds number is more than 4,000. First step is clear, right? Maria, is that clear for you?
Yes.
Okay, so once you get Reynolds number, next you will have to define your pipe roughness. To make it easy, smooth pipe. Okay, let's use smooth pipe. Okay, and the velocity profile I gave is only for smooth pipe. Okay, says smooth pipe. So then you can use Colebrook equation. Brazil's type of Colebrook is more accurate to get friction factor, right? Can you get friction factor? Yeah, once you get Reynolds number, you can get friction factor, right?
You said it's smooth. Why cold?
Because it is more accurate. You put roughness equal to 0. Colebrook and Brazil's type equation doesn't give you the same identical number. Which one is more accurate? Colebrook type equation is more accurate. Use that one. And you already know how to do it, right? And it appear in the exam, so you should not have any problem. Okay. So once you get friction factor, can you get friction factor over 2? Yes, you can. Can you take the square root of friction factor over 2? Yes. Can you multiply that by average velocity that you come up initially? Yes, right? Initially you may say, okay, your average velocity is 2 meters per second. Then you get this term, right? And that term is your V star, right? Good? Okay. You can get your V star, right? So I give you a function that V plus as a function of Y plus, correct? Correct, right? And y is the wall coordinate. It's capital R minus small r. Siri, you got that? Capital R minus small r is small y. Okay, so we have V star, right? Siri, yes? You can calculate V star. What about rho S? You have that already, right? Rho S.
Yeah.
Okay or yes or no, Siri? Yes.
Yeah.
No?
You give us oil density.
So first, you have to come up with your own. Who's not here yet? Everyone is here? Oh, I missed 11:05, now it's 11:06 and no one late, okay. So, tell me, Tope,
Yeah.
we need to come up with our own fluid property. So that's how you get rho S. You set it to a certain number. Good? Okay. What about you set it to a certain number? So you may say, okay, gas density equal to whatever you want, 2 kilogram per cubic meter. Liquid density maybe 900 kilogram per cubic meter. And you set your VSL, VSG to be a certain value, and then you can calculate your rho S, right? And you can calculate your mu S. Tope? Good? Okay. And then you can calculate Reynolds number based on the velocity inside the slab, right? Yeah, you get Reynolds number, you can calculate friction factor, and then you get V star, right? So when I say V plus equal to Y plus, what is that telling you? Velocity profile, right? Velocity as a function of radius. So let's say I try to plot velocity as a function of radius, right? So what I do is I set radius, okay, capital R. So capital R, let's say is 10 centimeter, 0.1. So small r equal to 0.0999. I can set it like that, right? Oh, let's zoom in a little bit. This is not homework review session, okay? It's for those of you who made your attempt already, and I explain a little bit more. Not have never done anything and wait for this session. So you can do this, right? Okay, let's say this capital R, and this is your R. Okay. So initially R equal to capital R. Okay, and I reduce it a little bit. Okay, reduce it a little bit. Oh, too much. So if I can get velocity at every radius, I'm done for velocity profile. Good. So from my small r, can I change to y? Yes, of course. This is equal to capital R minus small r, right? This is my small y. Good. So I get my small y. From small y, can I get y plus? Yeah, so I open the formula. Formula for y plus is small y multiplied by v star, which you already have. Multiplied by rho s divided by mu s. Good, right? So you can get y plus based on small y. From y plus, you can calculate v plus, right? V plus, for y plus less than 5, v plus equal to y plus. Done, right? In the homework, I give you the velocity profile. For v plus, y plus greater than some value, you have this kind of equation, right? So basically, we put the value of y in, and we get v plus as the output. Correct? Input is y plus, output is v plus. From v plus, can you convert it back to regular v? Of course, you multiply v plus with v star, then you get regular v. Then you can plot regular v as a function of regular r. That gives you velocity profile. อย่างเช่นนี้ where you get stuck. For the laminar case, you can set your own viscosity, density, right? And you can say, okay, angle is 0. If you set it 0, horizontal flow, you can set it like that, right? And you can come up with your own average velocity, correct? And maximum velocity is twice of the average velocity, right? So you get maximum velocity automatically. Good? If you don't like this idea, you can come up with your own average velocity. Then you can calculate pressure drop for the case of laminar flow, steady state, right?
Question 2.
Equation is given. Charge furthermore.
Should we derive it or we can get the integral?
You don't need to derive anything. You can say average velocity is half of the maximum velocity. If you
Is it true for laminar, just laminar?
just laminar flow, not turbulent flow. For turbulent flow, you have to follow the lecture. Everything is already lecture. For turbulent flow, that's what I worry about. Okay, for turbulent flow, it is exactly like this. Did you try? Did you try any of this? Very good. Oh, okay. Anders, you try?
I derived
You derive this. Do you get this line? Same? So I did it fine. Okay. Did you do this kind of plot?
No, I haven't.
You haven't done it. You will do it later. But no problem, right? You hope so. So how long does it take to get until this line?
I was a bit confused by when you changed the integration units, but I think I figured it out.
But eventually you figure it out. That's the point. Okay. Eventually you get it done correctly. Okay. Where's Jia Cheng? Can you text her? Tell her, come. It's late, but come to class. Alright. So you get this equation, C, small c, right? So we have to plot it against Reynolds number in the slug body. How can Reynolds number in the slug body has anything to do with this? We will change R plus. What's this? And yes. So R plus is calculated based on what? Reynolds number? Does it take Reynolds number? Seems to be yes, right? Your answer is yes. So it's Reynolds number over 2 multiplied by square root f over 2. So it has something to do with Reynolds number, right? So when your Reynolds number change, R plus change. Actually, V star change, right? V star is f over 2, and f comes from Reynolds number, right? So it will change. So when your Reynolds number change, V star will change. When V star change, everything else change accordingly. So if you start with your Reynolds number equal to 4,000, you get everything. You get C value. Can you copy the whole thing, duplicate it, and make Reynolds number equal to 8,000, 12,000, 16,000, 20,000? So you get several points, right? Then you can plot it like this. No problem.
Can you go to the next?
And you should not have any problem because this is identical to textbook and mine. Yes?
In this one, you have Reynolds number of slug body different than what you have down there.
Okay. RELS.
Yes. So
RELS. The equation in the book. Okay, this is what I plot versus RELS. This is what I plot. Okay, versus RELS. And I plot it again, but I use equation in the book, but not exactly in the book. I use this one, RELS. Okay, so 3.100 give us 3.100 is this, right? RES. That's 3.100. I cannot plot that. So I plot this instead, RELS. When I plot RELS, it looks like that. I try to estimate it because I cannot plot it.
So going through the main equation for C.
Main equation for C is this one.
So
this one.
Yes. So R plus, in calculating R plus,
Yes.
you need the random number of slot.
Yes.
Not LS.
Not LS.
So if I want to make, so this function is dependent on RES, not RELS.
Correct. That's February 1994 plot, RELS. And I want you to put against RELS. But if you know,
But it is a function of RES, not RELS.
the equation in the book is a function of RES. RES and RELS, they are dependent upon each other because V slab
Main equation,
and VM.
not this. Talking about the main analytical equation that we derived.
This equation,
Yes. So R plus
is this a function of RES or RELS or both?
It is RES.
Okay. What if can I have RELS change without changing RES? Probably not, right? They are kind of dependent upon each other. The only difference is rho and mu. The rest is the same, right? VM is the same as VS.
So why didn't you plot it based on RES so you can plot the main equation up there 0.021? So both of them on
Okay,
x-axis.
let me ask you this. Equation in the book, it is like this, right?
Yes.
How do you convert from RES to RELS?
I'm saying why at the first place you didn't plot it against or versus RES.
Because I cannot compare with the book. The book is in the form of RELS, right? Of course, our equation is a function of RES, not LS, right? But in the book, it is like that. So I try to compare against other people's results. And I see that, yes, it's kind of matched. Okay. I didn't plot against RES because the solution is not available. So I try to compare against the available solution. Best judging? Okay, university skills, right? For sickness. Okay. Alright. So try to do it. It takes some time. Arya, did you start?
Plotted the velocity profile.
You plot the velocity profile. How long does it take for you to do that?
Because it's at 10% of the numbers.
How long does it take for you to do that?
45
5
minutes.
minutes.
No, 45.
45 minutes. Okay, not 5 minutes. Okay. But you can do it faster than Arya, right? Don't worry about that. It will take 45 minutes. Anders, how long does it take for you to get this equation, the final form of C?
I don't know, 1.5 hours.
1.5 hours. Okay. Yeah, so you have 4.5 hours more to go, right? Alright. How long does it take for you?
I couldn't get it to work. I mean, for the box at least. I tried using that C over 0.02. It goes up, right?
Let's go up, yeah.
I then searched for the fiber paper. He didn't plug it myself.
Do you believe me? You believe this paper or you believe yourself? You should believe yourself.
This is the equation for that curve. Not that one.
Okay.
So it's different.
Yeah, it's kind of different.
Slide it in. Slide it in the wrong.
I don't know. You try and tell me which one is correct or how to do it correctly. I have already told you that when I actually plot, I didn't get the same thing. If when I plot RES, I have already shown you, if we plot against RES, so when I convert RES to RELS, I show you this, as RELS approach infinity, C value doesn't approach 0.2, but in the graph is approach 0.2, right? C value or C0 approach 1.2. C0, 1.2, which means small c is 0.2. But I show you that the equation I get from the book, it approach infinity. So it's wrong, for sure, okay? It's wrong for sure. Do we ever use that equation? No, we just say if it is turbulent flow, we use C0 equal to 1.2, done. Just like that. And you are about to see by yourself whether I tell you some wrong information or what I told you is correct already, or you cannot even determine whether I told you the right thing or wrong thing because you cannot repeat. Tell me topic, yes.
Sure. Can you go to the previous chat?
What?
Can you go to the previous chat?
Okay.
Yeah. What did you do to make to arrive at this? Because when I plotted mine, it was going up. So what did you do to arrive at this? Let's talk about that.
To arrive at this, I can calculate C value, right? So I change the way I calculate C value by changing liquid velocity. Keep changing liquid velocity, keep changing liquid velocity. The gas superficial velocity stay the same. Keep changing liquid velocity, so you end up something like this. Try more. If it doesn't match, this means you're right and everything else is wrong, okay? If what you did is correct. But tell me which one is what we should use. This chart, which is the same as this equation, or you want to use equation 3.100. Tell me. And also do it for laminar flow too, okay? So of course you have 4.5 more hours to do, right? For today at least. Take some time for you to do it. Okay. And next week, what do you have next Monday? Exam. Okay. Next week we have exam. Exam is weight less than the homework. It's like 6% and homework is 10%, right? Keep doing your homework. Okay. Exam, open book, open note. You can bring your previous formula sheet. Alright, last time we talked about the calculation tip. Okay, how do we calculate tau or all those things? The reason that we do all this is to get pressure drop, right? Just to get the pressure drop. Okay. So I give you the discussion about equilibrium level. Okay. Equilibrium level, we have the height doesn't change with the when height doesn't change with the distance, then we get equilibrium level. Okay, so film height stay constant after this point. Okay, numerator go to 0. The top part go to 0. Okay, and this is the top part, right? Tau f minus something. You still remember Dukler Hubbard? What is the top part? Dukler Hubbard equation. This one. Remember this one that we derived? Use Leibniz rule and do everything. We get this equation, right? Yes? Sweta? Yes? Okay. So we talk about equilibrium level. And We discussed, right, why VLTB should equal to 0. Sweta, why is that? Can we have VLTB equal to 0? Or when do we have that?
When it is allowed to
Okay, yes, yes. So away from the back of the slug body, we can have VLTB equal to 0. And it is possible. So I have already discussed, right, whether x is constant or change with distance. Akin, x is constant or change with distance. Change with z. Z is this coordinate. That is z. Z is over here. So x shedding rate, is that a function of z? Yes or no? No, it's not. Okay, it's constant. So x is constant. It's not a function of z, not a function of position. So this part VTB minus VS multiplied by HLS, it is constant, right? And it is something related to x. So we have, if HLTB go up, then the relative velocity has to go down to make everything stay constant. If the relative velocity go up, HLTB has to go down. Yeah, what is HLTB? I didn't hear anything. Liquid height? Liquid hold up. Okay. Of the telepable zone. Okay. So for the case where we have inclined flow, theta greater than 0. Okay, for theta greater than 0, we find the equilibrium level by set the numerator equal to 0. You see this numerator, set it equal to 0. Okay, so I put here that for theta greater than 0, tau film is 1/2 f rho absolute value of v multiplied by v, okay, equal to put this to the right hand side. Okay, I have AP h rho g sine theta divided by SF. Did I do it wrong? No answer. Okay, so let's take a look. I have VLTB. So Sweta, what is the direction of VLTB? Positive z or negative z for VLTB? Yes, backward to the floor. That is the direction of z. Oh, okay, that is direction of z. Okay. I put absolute sign over here. Okay. Typically what we do is we move this to the right hand side, right? Divided by -1. So I have tau s equal to minus AP something something something. So it's correct, right? Okay. So now let's take a look closely. VLTB, so it is positive for the case of backward flow. If we have it flow backward, VLTB will be positive. Okay. And no. This term say VLTB in the absolute sign. Okay, VLTB in the absolute sign. Absolute sign always give you a positive value, right? So the right hand side, sine theta greater than 0, sine theta give you kind of positive value, right? G is positive, H hold up is positive, A pi is positive, friction factor is positive, S is the distance is positive. So everything here is positive. Okay, and that is positive. So then we have VLTB to be negative. Okay, so let's take a look at this equation one more time. The top part that we get here is from numerator part of Dukler-Hubbard model, right? Minus tau F SF minus AP H rho G sine theta. That's the top part. When we try to find equilibrium film height, we set it equal to 0. When we set it equal to 0, so this is what we get. And we get VLTB less than 0. This is for Z greater than Z that equilibrium liquid height occur. Okay, so equilibrium liquid height occur at some location. Beyond that location, this is that Z. So beyond that location, we have VLTB to be less than 0 or backward flow. Is it backward flow or still forward flow? I have VLTB less than 0. So VLTB less than 0 for theta greater than 0. Does it make sense for you? Not quite. Just reading some equation to you and not quite understand. Okay. We have equilibrium liquid height when a certain distance from the back of the slab, right? Then we have equilibrium liquid height. A certain distance from the back of the liquid slab, we have equilibrium height. So this equation tells us that it is equilibrium liquid height. At equilibrium liquid height, okay, at equilibrium liquid height, the numerator goes to 0. Okay, at equilibrium liquid height. And at that location, I substitute the value for tau in, which is this one, right? Tau equal to minus AP over SF. I substitute the value in and I show you that at equilibrium liquid height, VLTB is negative. Okay? Negative means it's negative of Z. So it's flow in the same as the flow direction at equilibrium liquid height. Okay? So if we have Z greater than Z at equilibrium liquid height, okay, look at this carefully. If we have Z greater than Z at equilibrium liquid height, this means we far back from the height. So let's say equilibrium liquid height over here. And this is Z at H equal to HE, right? This distance is Z at H equal to HE. So for Z greater than that, so it's somewhere in this part, right? Okay. For somewhere greater than that part, what we have is, so for Z greater than that, do you think liquid height will be getting any smaller and smaller and smaller, or it will go up? Or what do you think, Arya? What happened to the liquid height after the equilibrium height?
It's smaller.
Gets smaller and smaller and smaller. That's probably what you have seen, right? That's probably what you have seen. Not supposed to go up, okay.
I'm asking if it's not supposed to go up because the next slot starts coming in. To see if it's not starts picking up.
Okay, let me tell you this. It's not about whether it's supposed to go up or not supposed to go up. It is about Dukler-Hubbard. It's only for the case where theta equal to 0. That's Dukler and Hubbard. If theta is not 0, Dukler and Hubbard model doesn't work. Okay, Dukler and Hubbard is for theta equal to 0. Even though they have theta in their equation, but it doesn't work. It is only for horizontal. So when that thing equal to 0, we have equilibrium liquid height. Okay. Beyond equilibrium liquid height, what did my equation say? Okay, I'll show you later. Let's do this. Okay, go to the next one. VLTB square. Take a look at this term. VLTB square is VTB minus VF, right? VF is the relative velocity, and by our definition, VTB minus VF is VLTB, correct? So this term square. This term square is this part, right? Left hand side. And the right hand side, I remove the negative sign because square thing has to be positive. Okay. And I said this part is only a function of HF. Okay. It's only a function of HF. HLTB, liquid hold up, is a function of liquid height. Right? It's a function of liquid height. SF is a function of liquid height. Right? So this part is only a function of liquid height. Okay. And VF is X over rho AP HLTB. X is constant. Rho L is constant, AP is constant, HLTB is a function of liquid height. So this equation is only a function of liquid height. Okay? It is only a function of liquid height. Then we have one function with one unknown, one equation. It can be solved numerically. Right? It can be solved numerically to find out what HF give me left hand side equal to 0. We can solve it. Okay. Alternatively, you can plot VLTB square minus 2AP HLTB sin theta over this versus HF. Okay. And whenever you get this part equal to 0, then that is the height, that is the liquid height. Good? Okay. So I think you have you seen the film moving backward yet? Flow with the film moving backward in the lab. You have seen, okay, I don't show you any of that, okay? You have seen it in the lab already. And did we go through this? Liquid height does not need to be there. It doesn't need to exist. We may or may not have equilibrium liquid height. This one is critical level. Equilibrium liquid height, we may or may not have equilibrium liquid height either. And I will show you why. Okay. Let me ask you this. When we have slug film, how long should be the film? As long as you want or what? In other words, when do we stop the integration? Arya? When do we stop the integration? This will can go on and on and on, right? When do we stop it?
You have the frequency, right?
Okay.
So can you get that frequency that one of the inputs?
It's one of the input, yes. From frequency, where we can calculate slug film length. So we will stop the calculation when we reach the film length. Okay, we stop the calculation when we reach the film length. Let's say the film length is not long enough. So if film length is this short, we may not see equilibrium liquid height, right? Correct? If film length is short enough, we stop the integration before we reach the equilibrium liquid height. That's possible, right? Okay. For film length is very long. If we have very long film, we can reach the point where height is the same as equilibrium liquid height. Okay, next one is critical level. Critical level, we do that by set the denominator equal to 0. Set the denominator equal to 0 and solve it numerically. George or Demo, how do we solve it numerically? This equation. How do we solve it? Okay, tell me Tope, how do we solve it numerically? We try to solve for what?
For H of 0.
You can solve for that too. But typically we solve for small h. But small h and HLTB is kind of the same thing, right? So if we can find HOAP, we can always find height. If we find height, we can find HOAP, right? Okay. So tell me Tope, how do we solve for HLTB that make the critical level happen?
Say we integrate.
Integrate. We set the denominator to be 0. Okay. We set it to be 0. And we have to solve one equation, one unknown. And you said our unknown is HLTB. Right? Then can you solve for it? One equation, one unknown. Find HLTB that make left hand side equal to 0.
Yes. No, explain. What explain?
X squared. Is it constant or it's not constant?
It's constant.
It is constant, right? Which equation in this book that you calculate x squared to me Tope? Who else has a book? Akin, okay, which equation that you can get x squared? 3 point what?
Small x squared.
Small x squared. Not Lockhart, Martinelli parameter, no, not that one. Which equation?
3.92.
3.92? Really? Are you going to do that? I don't think I want to do that. Which one? You know how to calculate x?
There's 3.88.
3.87? Let's use 3.87 because it's easier. VTB minus VS, that's what you can get, right? VS is the same as VSL plus VSG. Okay. Rho L, given fluid property, right? AP, given pipe cross-section area. HLLS, 0.6. Not 0.6. If you don't use 0.6, you get it from closure relationship. 0.6?
We just use the pseudo no slip holder.
No slip hole up inside the slug body.
Yeah, because
Can you use no slip hole up inside the slug body? Do you know VSL inside the slug body?
say we know VSL plus somebody. Yes.
Do you know VST inside the slug body?
Yes. And you layer it, right?
Really?
You did that. You
So VST at the inlet is superficial gas velocity, right? Gas per inlet cross-section area. Okay. Gas flow rate per inlet cross-section area. That's what we have. Gas volumetric flow rate inside the Taylor bubble, and inside the slug body, are they the same?
no, but the summation is the same.
Summation between outside the slug body and inside the slug body, right?
Summation of gas and liquid is everywhere.
So if we try to use VSG inside the slug body, that can be done only if we know QL outside and QL inside. is the same as QL at the inlet. My point is it doesn't distribute evenly. QL, not QL, QG, gas flow rate distributed in the Taylor bubble and gas flow rate distributed inside the slug body. It may not be quite the same. I think that's why people use correlation to get the liquid hold up inside the slug body. It comes from the correlation or closure relationship. To solve this equation for critical height, I would do everything as a function of film height. Critical film height, okay, it will be easier. If I have film height, can I calculate hold up? Tell me to pay. Once I get film height, how do I calculate hold up? It is also in the exam, right? If I get film height, how do I calculate hold up? Which equation? Come on. Don't let me find before you. I get it already. How about 3.38? A altitude. 3.38. A altitude. A altitude is AL divided by D squared. If you multiply by 4 divided by pi, that gives us hold up, right? 3.38, equation for A altitude. You see equation for A altitude? 3.38, page 67. Come on, the exam is next Monday. Yes, that's equation. A altitude, you see that A altitude? A altitude is AL divided by D squared. But you want hold up, right? Hold up is AL divided by pi D squared over 4. So A altitude multiplied by 4 divided by pi give you the hold up. Okay, so let's go back to the screen. So you can express HLTB as a function of height. Okay, so HLTB square is also a function of height, right? Correct. What about HLTB prime? Did I talk about that earlier? HLTB prime equal to what? This one, right? That is HLTB prime. Slide 38. Did you start to print your slide? It is open book, right? Printing a slide. So this is HLTB prime or DHLTB by DHF. Right? And it is a function of HF. Correct? So this means everything that you have in the denominator, this is the denominator in Dukler and Hubbard equation, right? Everything that you have in the denominator is a function of height. It is one equation, one unknown. We can solve it for liquid height to get critical level. Critical level sometimes exists, sometimes it doesn't exist. Okay? It is not always that we have critical height. But if we have critical height, the slope over there is infinity. Okay, the slope over there is infinity if we have critical height. So you want to check and then set the boundary condition to be a proper boundary condition. Okay, by that I mean the boundary condition for height at z equals 0. Basically, we want to solve this equation. Okay, we want to solve Dukler and Hubbard equation, right? We want to solve this. To solve this equation, it has to start from a certain boundary condition. Okay, let me change the battery. Have question? No question? Get confused?